anyways, welcome everybody. And we have a very special speaker today, just like we've had every week. But I am very excited to introduce Vivian Yu because I've known her for a long time. And I have been a big fan of her research for many years now. So Vivian got her undergrad degree at Caltech. And then after that, she went to Hawaii, which is my alma mater too. So I actually met her when she was a grad student there. And I believe I was on sabbatical, but maybe I met her even before that. So while Vivian was a graduate student at the University of Hawaii, she also got prestigious fellowship to go and do some of her research at the CFA in Harvard. And I think that's when I met her. So anyways, I actually met her through her research before I met her in person, because she, I believe, was coming up with a different method to measure the distance to, I forget which galaxy, but she did a precise measurement of the distance to a galaxy, which I believe is still
M33.
Sorry?
M33.
Okay. So anyway, so what caught my attention was just how much attention to detail she had and how reliable her research was. So since then, I have been following her. I also had the honor of being in her thesis defense, which is when I realized what a good speaker she was. And well, maybe I won't give it away, but she always gives entertaining talks. Anyways, after that, Vivian went on to do a postdoc, and she actually had her choice of postdocs, but ended up coming to UCR, where she was working on TMT instrumentation and also working with partly with Barham Mobasher. So then she went up to the high redshift universe. And then again, I had the honor to be able to work with her as she got another prestigious fellowship with the University of California Chancellor's Fellowship. So she was working on a dual postdoc between UC Irvine and UC Riverside. After that, she moved on to UC Irvine, where she has been ever since, first as a postdoc, then as a astronomer or assistant astronomer researcher, I believe is the title. And so anyways, as I said, her claim to fame for me is that whenever you read a paper written by Vivian, you can be absolutely sure that it's right. Because she is what I aspired to be when I first became a Christian. Sorry, that was, I don't know why I said that. When I first became an astronomer, just the idea that if anyone read my papers, that they could know that they were right. That's what I was told as an astronomer at the beginning, and that's what I think Vivian is now. Along with a couple of people in the audience, I mean, I personally think that the Kona survey and the koala surveys are the absolute best thing that we have when it comes to high resolution studies of AGN. And so Vivian is a co-I of the koala survey, and I'm hoping that we get to hear a little bit about it today. And anyways, I'll stop saying silly things, and thank you for coming, Vivian.
Well, thank you so much for that really nice introduction, Gabby. I'm not really sure I can follow that up with my talk. And I hope that I keep enough entertaining slides in this talk for your taste. And I also wanted to thank you and Shabita for organizing the series. It's been really fun just connecting with all the AGN experts here. I've learned so much from all the speakers and all the discussions. And I want to apologize in advance, just we have roofers kind of try to fix our roofs in preparation for solar panel installation today. So hopefully you won't hear a lot of thump, thump, thump in my background. Okay, so I wanted to get started. So, given all the AGN expertise on here, I think I'd like to contribute to this series from primarily the galaxy mergers perspective. So I'll start, generically from this medal plot showing the star formation rate per co-moving volume as a function of redshift, where you can see that star formation activity peaked at redshift about 2 around what we call that cosmic noon. And if you break that down by galaxy population, you would see that what dominates most of that star formation rate density beyond redshift of 0.7 or so is a population of galaxies known as the luminous, here in the orange, and also the ultraluminous infrared galaxies in the red. So just what are these lurks and ULurks, and how do they appear to govern star formation activity in our past? Some 30 years ago, when these galaxies were first discovered by the IRAS satellite, my PhD advisor, Dave Sanders, and others had put forth a theory for their role in galaxy evolution. So within this merger framework, you have blue gas-rich star-forming galaxies that come into close contact with each other, and they begin their delicate dance before merging and becoming a gravitationally bound system. And during this time, the gaseous and dusty material is driven toward the center of that system by the interaction, all while the optical light from the starburst is being reprocessed by the dust, and these galaxies then appear to be luminous in the infrared. And gas is then rapidly accreted onto the center supermassive black hole, and it triggers the AGN phase and also release of energy, which then subsequently drives out gas. And you're left with a gas-poor red elliptical that, depending on whom you talk to, likely evolves passively as the stellar populations age. And since then, we've relied on simulations to put this on a quantitative timescale, showing that this whole process takes place over the course of several giga years. And while these represent a relatively ephemeral stage within a galaxy's lifetime, the merging event introduces dramatic changes to the star formation activity as well as black hole growth within the system. And so I focus my research on these transitional objects in order to understand how galaxies evolve. Now, we've seen this M-sigma plot before in the seminar series, suggesting that despite the drastic differences between their scales, black holes and their host galaxies co-evolve, and that feeding and feedback have been invoked to explain this coevolution, but we don't really understand the detailed processes of how the galaxy and the black hole interface with each other at these resolved scales. And so if we want to understand what happens when galaxies and their central supermassive black holes merge, we need to observe gas-rich galaxy mergers, which are seen to exhibit these gaseous nuclear disks, 100 parsecs or so in size, in both observations and in simulations. And it's also in these circumbinary disks that we find supermassive black hole binary candidates, which are, of course, intriguing in the context of gravitational wave events to be detected by the next generation gravitational wave detectors like nanograv and IPTA as host to these supermassive black holes. So the bottom line is that we really need to understand the small scale environment which would directly impact the coalescence event of merging supermassive black holes. And right now we can only do so in the local universe where we have the ability to resolve physical processes in detail. So the key question that my research addresses is, how do supermassive black holes grow and merge? Now, considering the dynamic range involved, I break this question down to 2 different regimes. So on scales up to about a kiloparsec, how does that gas fuel the growth of supermassive black hole? And how does that in turn impact the surrounding? And on much smaller scales, just around the AGN, how does that inner nuclear structure come about? So in the interest of keeping this talk short to allow for time for discussion, I'll focus on the first topic during this talk. But if you're interested in extending some of the conversations from Misty's talk last week about using a velocity result reverberation mapping measurements to learn about broadline region kinematics in local Seyfarths, please feel free to ask me about the efforts and results from our latest lab campaign in a paper that I'm hoping to be submitting before the end of summer. And I know co-authors in this audience will hold me accountable for that. Bonus point is that my senior thesis student, Liam Hunt, has been analyzing the narrow line region kinematics in those very same Seyfarths using KCWI data to explore the connection to the broadline region. And he's going to be applying to graduate programs this fall. Let's get started. Here, I'm giving you a sense of the scale when I talk about the inner kiloparsec region of a galaxy merger. But you might ask, perhaps legitimately, why would the gas in such a small region within a galaxy even matter in a grand scheme of things? And the answer is that you really need to think of the galaxy not as a static entity, but as a dynamic ecosystem. So within a galaxy, you have your interstellar medium, which fragments and collapses into giant molecular clouds, 100 parsec or so in size, where stars are being formed. And you pick your favorite stellar evolution. Stars go supernova at the end of their lifetimes. And these stellar explosions then inject energy into the ISM, and they drive outflows and winds. And eventually the gas perhaps cools and fountains back onto the galactic disk. And perhaps there may be also some cold gas component from a large scale filament, and you get inflows of gas of new fuel for the next generation of stars. And maybe some of that gets funneled into the center to feed nuclear starbursts or black hole activity. And this in turn then might drive even more outflows. And if they're energetic enough, they might just expel the gas completely into the circumgalactic medium and subsequently quench star formation in the galaxy. So now, if the merger activity drives gas in a certain way that influences some of these processes, it will play a big role in how that galaxy evolves. And right now, we just don't know, for instance, the merger contribution to this process or the detailed timescale or energy deposition into the ISM that's taking place. And the complexity of this process in galaxy mergers is also investigated by theorists using, for instance, the Fire 2 simulations. This particular simulation here by Jorge Moreno and company looked at the star formation here on the left and the multi-phase ISM on the right during the merger process, where the different colors corresponds to gas of different temperatures. Now, although AGN feedback has yet to be incorporated into this particular set of models because of the complicated physics involved, nonetheless, we need comparisons to observations of gas and stars at these similar scales to help provide constraints on these models. So fortunately for me, we live in an era of high angular resolution studies across the electromagnetic spectrum. Here, I've listed the resolving capabilities of some of the current and upcoming facilities that highlight the level of details we can get down to right now. But what I really want to highlight is some of the work that we've been doing with ground-based AO instruments, particularly those on the Keck telescopes. So to demonstrate the power of our Keck datasets, I want to first demonstrate with a case study where the different science topics we've been able to learn using these near-infrared integral field data at high resolution. So here's Macquarie 273, which is my favorite pet ULERC. That is also a late-stage galaxy merger with a very complex nuclear region. And we've observed this galaxy with OSIRIS on Keck and have data very complementary to some of those in the Kona survey that Francisco had presented for local secrets a few weeks ago. And if I slide across this H-band spectrum with the iron 2 line here, you can see really well how the iron 2 gas is rotating. Projecting this onto the 2D form, here on the left is the flux map showing the distribution of the integrated iron 2 gas in the nuclear region. And you can see it's very complex. It peaks at this clump here, but we also have some sources on the north and the southwest. The velocity map, and the contours that are overlaid are from the continuum. The velocity map depicts a Keplerian disk rotating this way. And because of the high resolution capability, in this case, 28 parsecs per pixel at a distance of redshift 0.04, this allows us to actually resolve within the black hole sphere of influence. And so we can compute the dynamical mass of the source sitting in the center of this gas disk. So by modeling the rotation of this gas, we find that the mass enclosed within this tiny region could be about a billion solar masses, which agrees really well with a previous estimate based on OH masers. This agreement was a pleasant surprise, particularly given how, as Misty explained last week, that the issues that might arise with using different tracers for different dynamical mass modeling. And this also lets us argue in favor that this is in fact a compact remnant nucleus rather than nuclear star clusters, as some had previously claimed. I should remind you that many folks, including present company here in this talk, have been measuring dynamical masses in nearby galaxies directly for some time, even though it's not a trivial observation to make, and can only be done in nearby galaxies where you can resolve the collective motion of gas within the black hole sphere of influence. But extracting, useful kinematics in these messy cores of mergers has been a different type of challenge. And we're really trying to do the best we can, lending insights into how supermassive black holes may be growing during this merging process. So when we looked at a sample of these galaxy mergers with OSIRIS during the initial stages of our observing campaign, which preferentially covered late-stage mergers, we found that stellar and gaseous nuclear disks were nearly ubiquitous among these late-stage mergers. They tended to be dynamically young and were likely to have formed in situ during the merger process with effective radii of a few 100 parsecs or so. We used the near-infrared tracers such as the CO band heads and also the H2, molecular H2 and ionized gases that fall within the K-band coverage for the measurements. And these results were a bit of a surprise, actually, given that we found these rotating disks at the center of these messy train wrecks, and that also allowed us to make black hole mass estimates within these merger nuclei. So I showed this M sigma plot earlier, signifying that black holes and their host galaxies grow together somehow. But when two galaxies merge, do these quantities still grow together, or does the black hole grow first and the bulge catches up, or vice versa? And so now we're finally able to answer this question by putting dynamical black hole masses for galaxy mergers on this plot. And we found that they tend to lie on or above black hole scaling relations. And so at the time, we favored a couple of these interpretations. One is that supermassive black hole growth takes place rapidly, thanks to the infilling of gas and precedes that of the bulge. Or that there are just large gas reservoirs resting within the small enclosed space, ready to fuel the supermassive black hole. And so in an attempt to differentiate between these scenarios, we've since obtained ALMA band 6 data at comparable or better resolution than the near-infrared data for one galaxy, NGC 6240, and computed the nuclear gas mass. And on this plot, 6240, we actually determine the mass for the two nuclei separately, the two AGNs separately in the purple and the light blue here. And we found that the correction was less than about 10% for the northern nucleus, but spans a large range for the southern nucleus, slightly depending on the tracer that we used. So over here. And so, yeah, at the moment, we're trying to expand our effort to other galaxies to see how that correction factor may vary across a sample. And my own personal feeling is that this depends a lot on the gas content around each of the nuclei. And of course, these particular colored points only really represent a few of the late-stage mergers that we targeted in the earlier part of our CAC campaign. Since then, we have more than triple the number of data points on this plot, and hopefully we'll be pushing out a revised version in the near future. But what's more is that, observing primarily in the K-band, we've probed a suite of near-infrared diagnostic lines that feature several row vibrational transitions of warm molecular gas like molecular hydrogen at about 2000 Kelvin or so, and also hydrogen recombination lines like bracket gamma and delta, along with other gas species like the corona line that we've heard about previously, silicon-6, helium-1, etc. So note that this particular plate scale here, 0.1 arcseconds per spexel, is comparable to that of near-spec abroad JWST. And I'm going to come back to the synergy with JWST later in this talk. So back to McCarran 273, previously combining multi-wavelength data and literature with relatively shallow 44 kilosecond Chandra data. So we're looking at the soft X-ray band here, and then this is an underlying infrared image with radio continua. We really only had evidence that one of these clumpy components is an AGN, and that's the southwest really red nucleus. The northern component is actually extremely Compton thick. And it wasn't until our Keck observations that led to the discovery of this dual supermassive black hole system, with the dynamical measurements supporting the northern source being a nucleus, that the dual nature is further confirmed by subsequent deep 200 kilosecond Chandra data that we got more recently. So having that gas kinematics, not just the high resolution imaging capabilities to resolve them, but also learning about the nature of that emission is really useful in finding and validating the dual supermassive candidates, the supermassive black hole candidates. So what's more is that when we looked at the kinematics of the molecular hydrogen, we saw, it looks different from the iron 2 morphology that I showed before, although you also get that very similar kinematics, but we also saw signs of biconical turbulent gas in the velocity dispersion map, which gives the smoking gun signature of molecular outflows observationally. And we interpreted this as gas being jetted out of a central obscured source in the middle of a rotating disk, and we determined its properties like velocities and mass and energetics. And these are crucial numbers that could be used to constrain simulations at similar resolutions quantitatively as the first glimpse into how AGN feedback might be at work at the very center of these dust obscure environments, hopefully somewhat close to the launch site. Now, McCarran 273 is one such interesting object. We've actually observed a whole sequence of these galaxy mergers in the nearby universe in very similar vein. So together with Anne Metling, Claire Max, Gabby, and other collaborators in the GOALS team, we've conducted a Keck OSIRIS campaign to target specifically the gas and stellar kinematics in these nearby emerging systems to study the feeding and feedback processes at very small scales. Please feel free to check out our website if you're interested in learning about more details. And I'll note that this is very complementary to the GATO survey that Christina talked about some weeks ago. So it's great that we've got cats and koalas talking, looking at multi-scale and multi-phase feedback all together. So in a nutshell, our koala survey covered about 30 some nuclei in the 26 systems where we're resolving gas and stellar dynamics at a few tenths of parsecs. And I briefly discussed nuclear disk properties and black hole masses. Our latest survey paper focused on feedback at the nuclear scales. So for instance, we've determined the extinction corrected nuclear star formation rate based on bracket gamma. And we noted that it does increase with merger class or decreasing separation between the nuclei. In this paper, we've also found that shocks as traced by excess molecular hydrogen are more prevalent in the AGN hosts. Now, this by itself may not be surprising if you expect AGNs to be driving shocks. However, they don't seem to actually correlate directly with AGN strength as being measured from mid-infrared or bolometric AGN fraction very well. And that's something that we might need JWST to address as well. Okay. So now I want to show you some ongoing work and our latest preliminary results in multi-phase outflows. So we've seen what the warm 2000 Kelvin molecular hydrogen gas looks like at these small several hundred parsec scales, and simulations have predicted how the mass, density, and temperature of the gas evolves as galaxies interact. So observationally, we'd like to test this interface between the multi-phase gas. Here I'm showing you another really interesting galaxy. This is 3Zwicky-35, and this is an early stage merger, modest luminosity alert that is actually atypical among the nuclear outflow hosts we've identified in our 2019 paper, where most of the other outflow candidates are ultraluminous AGN hosts. But 3Zwicky-35, on the other hand, is not detected in the hard X-ray by SwiftBet, and is a competitive candidate, perhaps based on its mid-infrared spectrum and really compact core at 33 gigahertz. We've also previously measured the dynamical mass of the black hole to be several hundred million solar masses. When we observe this with Keck, the OSIRIS observation, which only targets the central 1/2 arcsecond region, shows very prominent warm molecular hydrogen emission here on the left, that's offset from the peaks of the bracket gamma emission on the right, as well as from the peak of the K-band continuum shown here in contours. The ratio of these lines, X over bracket gamma here in the left panel, measures shock exceeded molecular hydrogen in excess, while the differential velocity map on the right panel, where we fitted and subtracted that disk rotation from the H2 velocity field, shows outflowing shocked gas towards the edge of the OSIRIS tiny field of view. So what we wanted to do is, of course, measure the full extent of this extra outflow and see its influence on the galaxy, etc. And so we decided to get a high-resolution narrowband image of the H2 gas with a wider field of view using NERC2 with AO on Keck. And yet, the H2 emission remains just a bubble, 200 parsecs or so from the nearly edge of the disk. You can see some additional diffuse molecular hydrogen gas on the far side. And it turns out that there's actually an asymmetric bipolar outflow detected in CO1 to 0 from NOEMA at 1 arcsecond resolution, with velocities up to about 300 kilometers per second and similar morphology as to what we're seeing in the near-infrared. At the same time, we've gotten some high-resolution ALMA observations of the CO2 to 1 gap at a tenth of the NOEMA resolution. Now, if you look at the moment 1 and moment 2 maps here, you can see that the kinematics is consistent with there being extended outflowing gas away from the central rotating gas disk. And so putting this all together, here is a 3-color image showing the integrated warm molecular hydrogen in green, the blue and the red wings of the CO gas in blue and red, respectively. And the cooler CO gas appears more extended than the 2000 Kelvin H2 bubble, part of which may be entrained in the larger gas flow. So we're currently doing some work to properly compute outflow rates and masses, but a simple descriptive scenario may be that shock-heated molecular hydrogen is being entrained in outflowing gas, CO gas that originates from a central source inside the disk. But we still don't know what the nature of that central source is. As I said, it's not as clear-cut as we would hope that it would be. So this summer, my colleague Loreto Barco Munoz student, Mino Rodriguez, have recently generated this high-resolution spectral index map here on the left, and the corresponding error map on the right, using ALMA Band 6 data. And they found this clumpy structure situated inside the disk. And bear in mind that all of this region actually falls within just this tiny region of the disk right here. So the scales here are tiny relative even to the molecular gas that we've been discussing, where these clumps are only about 60 parsecs or so from the center, which is this clump. And in particular, if you look at the color bar, the negative spectral index at the central clump may be indicating synchrotron emission from jets. We can maybe make out some jet structure a little more. We need to spend a little bit more time looking at analyzing this data. And that will support the scenario of an AGN deeply embedded in the nucleus. Here's some never before seen footage of new KCWI results that I literally just got out of the pipeline last week, partially for this talk. Here on the left, you can see the much bigger spatial coverage of the KCWI field of view. And here on the bottom, you can see the optical spectrum featuring very prominently the O2 line. And it has this really interesting loop structure that is aligned in the direction of the H2 bubble and the blue side of the CO outflow that I've been showing you. I haven't had a chance to overlay it on top of our other multi-wavelength data yet, but I've roughly measured this to be about 3 kiloparsecs out from the nucleus. So this is about 10 times larger than the extent of the CO outflows that our data was sensitive to. We're currently in the process of running spectral line fitting to look at the ionized gas kinematics in hope of figuring out whether this is in fact a loop, or is it a bubble or hollowed out shell, and how it may have interfaced with the much smaller molecular outflows that we've detected. So my incoming postdoc at UCI, Adrian Bittner, will be working on the analysis of this and other KCWA data that we've collected of these ghost galaxies using the GIST package that he has written. So this one case of an early merging moderate luminosity LIRG showcasing a molecular bubble 200-300 parsec or so in size with a dynamical age of less than 2 million years, while featuring extended ionized outflows, some 3 kiloparsecs out. It offers a great laboratory to explore this multi-scale, multi-phase feedback phenomenon. And especially that it provides potentially that missing piece to understanding how AGN feedback starts out, since we get to image the system so close to the launch site, and perhaps, while the AGN might still be in the deeply embedded state. But at the same time, as you recognize, it also probably brought us more questions than answers. There's still a lot to be learned in terms of how the gas may be interacting with the circumnuclear depths, or if the outflows entrain metals in the ISM, or if it really even hosts a young AGN. And so to further answer these questions, we turn to JWST. So as you all know, JWST will achieve an order of magnitude or 2 better in sensitivity than Keck at 2 micron or Spitzer at 10 micron. And this is huge given how much more we'd be able to peer through the dust into the very center of these dusty galaxies. But what I'm most excited about is that we're putting a mid-infrared integral field spectrograph in space for the very first time. The MIRI coverage probes a slew of these pH and cooler gas features, about hundreds or so of Kelvin, in nearby objects. So between the GOLS ERS program that's led by Lee Armis and also my GEO1 program, we're going to be observing the nuclear region of about 10 such nearby LIRGs and ULIRGs that span a range of silicate strengths to take apart the multi-phase chemistry in these dusty nuclei and to hopefully provide the complete story of feedback in these extreme environments. And I would be happy to tell you more about the observations of either or both of these 2 JWST programs if you're interested. On a related note, I'll likely be posting in postdoc at later this fall to the first this JWST week. So please feel free to pass on the info to any potentially interested candidates. And before I wrap up this part of the talk, I wanted to just quickly advertise the work of Tianmu Gao, my visiting master student from Beijing Normal University. So as part of my NASA ADAP program, which I didn't have time to discuss here, he's been generating inner 100 parsec nuclear SEDs using multi-wavelength X-ray 2mm high-resolution images, looking specifically for luminosity or merger stage dependent trends in the nuclear SEDs, and looking at whether or not the multiple supermassive stage mergers actually experience similar growth pathways. So hopefully he'll wrap up his writing in the next couple months before the grad school application season. So just to summarize this part of the talk, I've discussed the insights on feeding and feedback processes our koala survey was able to reveal. And most importantly, we can see direct observational evidence for how supermassive black holes and their host galaxies interface at these tens of parsec resolutions as the merger sequence progresses. And this sets up really well for what we may learn with JWST. In the last few minutes of the talk, I'd like to actually discuss dual age supermassive black holes as an exciting future outlook. So, as an observer, I think that our next decades of discoveries will be tied to the capabilities of upcoming observational facilities. As a couple esteemed astrologers on Twitter have noted, we're rather excited about some space Ouija board and extremely large crystal ball. I've already talked a little bit about the former, so let's focus on the crystal balls here. And I think this particular audience won't need an introduction to the next generation 30-meter class LTs. As Gabby mentioned, I've got involved ever since my days as a TNT IRMS postdoc, writing exposure time calculators and doing data simulations for AO-assisted spectrographs on the TNT. And I've since stayed within the US ELT community and helped with emphasizing their capabilities in several decadal white papers. So in particular, we've highlighted some supermassive black hole related breakthrough science cases that we hopefully expect in the next decade, including those of dual AGNs. And I'm sure we're all anticipating the Cato results to come out any moment now. So I've shown this plot in the very beginning of my talk to motivate why we care about lurks and ULurks at all. And at the higher redshifts, unlike the local universe, it's a little bit more ambiguous whether this population is dominated by mergers. And I know that this is a very active area of research with lots of different results coming out. But I think there is evidence out there pointing to a significant merger fraction for the more luminous ULurks at high redshifts. So here on right, this plot shows the fraction of galaxies of various morphological types, the different colors, as a function of infrared luminosities. And you can see that at redshifts 1, up to about 50% of the galaxies might still be mergers with dual supermassive black holes. So I'm hopeful that we'd be able to find them with the right tools, but then of course the question becomes, can we actually detect them so far away? So here I've got a VLT Muse cube of a redshift 0 dual AGN with separation of 4 kiloparsec clipped around H alpha N2. And I've done a very quick and dirty simulation of what it would look like with kekostars at a redshift close to the cosmic noon, where that separation is marginally but detected perhaps still at low signal. And the next generation of extremely large telescopes will provide a resolution gain of close to an order of magnitude. These kiloparsec separation duals will become routine even far away. Just to visualize the parameter space that we're looking to explore, here's a plot showing the redshift versus projected separation for all the dual AGNs that were discovered using optical and other methods thus far. So with the next generation, I've used probing down to several milliarc second limits. We're going to be opening up this entire space for more discoveries. So just to summarize, I've demonstrated to you how we've learned about nuclear gas dynamics at small scales to understand the black hole feeding and feedback processes in mergers. And this really required a combined effort looking at different phases of the gas, different wavelengths, different scales, and making comparisons to theoretical simulations to nail down this picture. And I'm excited to see what we're going to get with JWST and also with the next generation 30-meter class telescopes to learn about supermassive black holes and mergers. So I'll stop there and take any questions you may have. Thank you.
Thank you, Vivian. That was a fantastic talk. I have a lot of questions, but I'm definitely going to let the audience ask first. So we already have a question from Stephanie. Do you want to read it or ask it, Stephanie?
Oh, sure. Oh,
I can just. Hi, Vivian. I really enjoyed your talk. This is great.
Thank you.
So my question was about you're presenting the Trees Wiki 35 object and then mentioning that it has a likely content thick AGN. So my question was whether we can distinguish between a content thick AGN versus maybe the AGN that switched off, that was like bright and switched off. And the reason I was thinking this is possible is from simulations, at least, there could be a strong accretion event that makes a big outflow, but that can actually quench temporarily the AGN itself. So I don't know if this is something that's possible to answer with. So I was curious to hear your opinion about that.
Yeah, that's a good question. Frankly, I don't really know. It's a short answer. I would think that it's possible. Maybe we can, from calculating gas accretion rate, to see, just exactly. I guess my a priori assumption is that this is an early stage merger. So, just from the morphology, we're pitching this as, well, it's starting to interact, but maybe there's not that much gas going into it yet. So in that case, my a priori assumption is that this is an quote unquote early stage merger, AGN, in this particular case. But that said, I don't know, right? I suppose it's possible to look at perhaps previous if there were previous observations that would point to this, and maybe if we actually do find a high attrition rate, then maybe we could say something about that. It is true that it is definitely intriguing scenario, I think, to think about.
Yeah, so from the outflow, because you were showing this O2 bubble that was 3 kiloparsec. So do you think that was launched by an AGN or starburst then?
Given that I just saw the loop last week, I don't quite have too much theory to back anything I'm going to say up yet. But I think, I can totally see, it could be potentially consistent with a previous episode, like it might be an alpha bubble from the previous episode, and then now with the new molecular alphas and is clearing this out. And so that would be entirely a possibility, and it's something that we would consider as we're moving forward in writing up this paper. So thank you.
I'm looking forward to see what your possible scenarios are. Thanks.
Yeah, thank you.
Just briefly before we go to Mike, I just had the question of, since we're talking about the bubble, did you see it in O3 as well? Or I know O3 was a lot weaker.
Yeah, it's not in the state that it currently is. Like I said, we're currently doing better spectral line fitting that I was able to do with a quick QFITS view look, and you can see. You can see that O3 it's much weaker. It's like right here. And so when I pan over to that line, I do not see the loop. I do see some maybe fainter extended structure. Hopefully, once I do the proper decomposing of the spectrum, that maybe we can see something to say more. That said, I will mention. I just have a slide here. Let me actually quit out of this for a second. Sorry, I do have a slide because we also have some WIFES data that is WIFES data. Where's my WIFES data? Here. No. Oh, dang it. Sorry. WIFES data. Okay. Let me share the screen. So we have some WIFES data, which compared to KCW, it has better spectral resolution and coarser spatial resolution that allows us to cover the entire thing. So this is, again, very preliminary. This is at 1 arcsecond pixel resolution. But this is also the blue and the red continuum. You've got, in terms of the O3, the sensitivity is quite limited, so we can't say much about the O3. But when we looked at the N2, we actually do see this extended feature. And this is, again, not a very good map that I'm showing, but you can see, when we looked at the contours, that you can see the extended N2 that is along the same line as the velocity dispersion that we're showing in this video. So I suspect that there is probably some, and the extent of the N2 outflows actually gets up to like 4.5 kiloparsec, so a little bit more extended than the O2 bubble that I was showing. But again, this is all very preliminary, so I'm saying all this with a grain of salt. But yeah.
Great, thank you, Mike.
Yeah, so I was actually going to ask more about 3CW. It was looked at by Spitzer and they didn't find Neon 5. Is that correct? Or and
I think that is true.
Yeah, that's interesting. I mean, I think you could probably place some fairly, tight constraints. I know it wasn't detected by SwiftBAT, and then we did like a special thing to look at all the lurgs and U-lurgs, but that was only at sort of, luminosities of 10 to the 43. But I think with Spitzer, you could, place really tight constraints on what the bolometric luminosity. So you could try and figure out whether it was maybe like a low luminosity, possibly Compton thick AGN, or possibly a higher luminosity. So that might be interesting. And then one other question was, can you go back to your like dual AGN separation slide? A couple of slides. It was like right before you ended, where you had it in parsec.
Yes. That this one?
You're
No,
sharing
I-
your whole desktop.
Oh.
I don't know if you mean to do that.
Oh,
It was
Here,
it
let
was
me,
like one where you had dots for each of the dual AGN that had been detected in with separation. It was like 3 slides before you finished. I was just curious. There was one at like 150 parsec. I was wondering which one that was.
yes, I know what you're talking about. Sorry, I'm temporarily incompetent with Zoom. Okay, was this what you're referring to? Was this-
Right. So the X's were ones. Oh, that was that. Yeah, the one you just had on that we switched from. Yeah. So which is the one at 120 parsec or something?
That is, let me think. I knew this at some point. So I know that this is NGC 6040, and I think this is the 4C plus 37 object. That is,
Right.
oh, I knew this at some point in time. I think it might
Maybe
be
it's
slipping my mind at the
3393
moment.
or something, or yeah. But that's okay. That's okay. I can look it up in the paper. I was just
Yeah.
curious.
Yeah, no, definitely. Yeah, because I know that at least for the nearby points, I had looked them all up at some point in time, but I forgot to review it just yesterday. But it's a good question.
Right. Yeah, and then one last, sorry, I'm doing like a 3-part question, but can you talk a little bit more about hope to find dual AGN with the radio? I haven't really done much in that space, but I think it's really interesting. I mean, you talked about synchrotron emission and other things, but can you get it also from like the radio SED and?
Yeah, so I'm not gonna claim to be an expert in the radio. I know, like, Jenny Green and others have done a lot trying to look for things from the radio perspective, and perhaps others here as well. But the I think I remember looking at the NGVLA papers when they came out in a batch a couple years ago maybe, and I think they talked about it's really the high spatial resolution imaging to find them, but whether or not we can identify candidates using SEDs, and I think synchrotron emission would be, obviously one way to go. And actually that links back to what I was going to say about 33835 when you mentioned it, was that what I didn't show is that we also have VLA data that Loretto has produced spectral index map. So the spectral index map I showed here was done from her student, but it was using a rather narrow frequency range. It was only with like the band 6 data with like the 2 sides of the continuum that we're able to probe. But she's actually done the similar spectral index map, but using VLA data, using K and is it X band or C band? I can't remember. But she and you also see the same like pretty similar morphology, but also the same negative spectral index. So we're obviously it could still. I don't know if it could potentially come from other radio supernovae remnants or not, but I think that is still at least some more evidence pointing to, or supporting rather, this quest that we're hoping to unravel the mystery of at some point. Thanks, Mike.
Okay, more questions? Matt.
I saved this because it's really somewhat peripheral, just personal interest. Could you show the SED slide from your student from Beijing was putting together? I know it's just very preliminary, but it illustrates something that's been on my mind for the last few decades, which is you're looking for signatures of AGN. Yeah, there's the SEDs at the bottom there, which might be very heavily obscured. And so a lot of things aren't going to go very good, like UV, X-ray, and so forth. Maybe they don't have much radio emission. So we're relying a lot on the near infrared, the excess of hot dust, which really, even if there's a lot of reddening, it's kind of a distinctive feature of a lot of AGN. So, and there you have IRAS F0725, both components. Now, this is not the model and whatever, but you often see like a rest frame 2 micron K-band excess there over what the stellar photospheres should be turning down, but it's actually going up from the AGN. The thing that, sorry, long question. I was wondering about is you also have a lot of pretty powerful starbursts that might sometimes be included in the beam too. Over the many years, I seem to recall that a lot of starbursts, no AGN at all, no accreting black hole, can have such amazingly hot dust right in those intense starburst regions that they can also produce some 2-micron excess there, which might be mistakenly identified by us, as coming from an AGN. So when you're model fitting SEDs, I just don't know if people include the full extreme range of possible starbursts that, could be out there. Or I don't know. And sorry, I know this is really quite a distraction from a lot of the beautiful stuff you're showing here, but it's just something I was wondering about.
No, I mean, this is obviously something I'm interested in since my student is hoping to wrap up this paper. I will say that we took a lot of care in comparing, these multi-wavelength images. It's really difficult, especially in these mergers, as you know, to identify where the centers are. This is actually a relatively clear case. I would say like there's something like 2,396 for those of you who are familiar with the system. Are there 2 mergers, 2 galaxies, 3 galaxies? We don't know. Like there's all the infrared luminosity is coming out of this clump that in the optical doesn't look like anything like a galaxy. So is it a 3rd galaxy? Is it just a Shakti that come? So it was a very difficult. This was actually the most time-consuming part of my students' project, was trying to match up the different nuclei. And we think at this point that we've done really the best we can to try to match up among the different nuclei, of trying to match the astrometry to make sure that what we're claiming as a nucleus is a nucleus. Of course, we're hoping to publish everything in the table. So, if people don't believe a certain point, you can feel free to toss it. But in terms of identifying, the nuclei, we hope we're centering in the right clumps. And then at the same time, that's partially why we're using a relatively small aperture. We're hoping to be able to eliminate the starburst contribution so that most of the emission that's coming from within the aperture we're looking at is dominated by the AGN. Now that said, I'm not saying that we're completely naive in terms of expecting there to be no contamination from starburst, and so and that's and the modeling is something that he was just getting into because he actually just got all those photometry in. Now we're looking at the SEDs, and so we're going to be looking at the different SED models and see compare and contrast, see which ones are better to use. Right now we're exploring the exagal model. We heard that that's a really good one for because it takes into account the AGN, the X-ray component, and how that can I wouldn't say extrapolate, but that goes across the entire electromagnetic spectrum. But the infrared excess and where we're having this distinguishing power is definitely where we need to be the most careful. And my student actually, he's so meticulous. He's like, I still want to check the infrared flux calibration for like the 100th time. So that's a really good point that you brought up. And so we're hoping to minimize this contamination from servers by looking at the smaller aperture, but at the same time, we'll pay attention for sure to the modeling that we end up using.
So, yeah, Misty.
Hi, Vivian. Thank you for a lovely talk. I want to take you up on your offer to talk about something that wasn't in your talk, which is the velocity resolved analysis. I think I noticed Markarian 110 in the little preview plot that you showed us. And I think if I remember right, that object has been claimed to be a super Eddington accreting massive black hole. And so I'm curious from your velocity resolved analysis whether you are finding that claim to be true, or if you have some information that you can share on that particular object.
Yeah, so definitely sharp eye. We did, for Markarian 110, I think our latest results of the velocity resolved measurements, and you can see from this plot that it seems to be showing a more symmetric structure in the velocity resolved map. And for this particular galaxy, we actually also have the KCWI data that my student Liam Hunt here has worked on, and the complication in terms of the slightly larger scale kinematics is that there seems to be two objects actually. Another one that's very close by. I'm trying to recall the scales. It's like several tick marks, but I need to remember what the this is not the final version of his map. I just kind of cropped it out. But and actually this map refers to 1392. He had another one for Mark 110. And it more or less seems to be showing also a symmetric shape in the narrow line in the O3 kinematics that he has analyzed. But it is complicated by the fact that there is a separate object pretty close by, so that can probably have some additional kinematics superimposed on top of the nucleus itself. But I would also say that Varda Bennett, who she and I were the ones who took the KCWI data originally, and we saw, and she's done a PPXF fitting of the data, and I think there is nothing out of the expectations, at least in terms of stellar kinematics. And so, sorry, I think I launched into this session, but I forgot maybe I missed your original question. I'm sorry.
Oh, that's okay. Yeah, I think that second object you're thinking about, I believe I saw a reference where someone had actually identified it as a field star in the Milky Way. So
okay.
It's, I think, just superimposed on top of it. And if I can find that reference, I'll send it to you offline. But yeah, I was thinking that I remembered that there had been claims that this particular AGN was a super Eddington accretor. And so with the velocity resolved analysis, hopefully, I don't know if you've carried out a full dynamical modeling of the velocity resolved results at this point yet, but that would give us an idea of the inclination effect on the black hole mass that is derived just based on a time delay and a line width, and would also give us a better handle on the sort of the calibrated black hole mass to compare with the bolometric luminosity to see whether or not we actually agree with any claims that it is super Eddington accretion happening in this object.
The answer is yes. By we, it's not me, but it's a Tommaso student, Elizabeth, who's going to be using Caramel to on this LAMP campaign, data from this campaign to basically run the dynamical modeling. So she will have answers for us all exactly addressing the very things that you said, hopefully very soon. So
Great.
Thank you for bringing that up. And that's definitely a very interesting object to pay attention to.
Sure, I'll stay tuned. Thank you.
Thank you.
I noticed that we still have several students and postdocs in the audience. So since you advertised for a future JWST postdoc position, would you care to tell us a little more about what you're looking for?
Sure. So this is basically going to be a position for a postdoc who will be working primarily on the JWST data from my GEO1 program. And there's some slight differences between I mentioned the ERS program and my GEO1 program. The ERS program focuses on 4 lurks from ULurks from the gold sample and looking at all the different modes, near spec, near cam, MIRI, etc. Because that's part of the ERS. As part of the ERS program, we wanted to be thorough and looking at all the different modes and provide that data to the community. For the GEO1 program, we're focusing specifically on MIRI. And so this is a case where, because we already have all this fantastic near-infrared data with Keck, that we think, while obviously JWST is going to go much deeper, but we wanted to focus our limited resources on probing, the mid-infrared, which we've never looked at before at these resolutions. So we wanted to tackle specific questions on understanding, the outflows, whether or not there's deeply embedded AGN in there, and looking at the different line ratio emissions and mapping out the H2 PAHs, et cetera, at levels that we've never seen before. So I I'm hoping that, the postdoc would have, insufficient, I guess, maybe IFU skills to feel comfortable jumping into JWST MIRI data analysis. We're also currently, obviously in preparation for the data that we'll be getting, we're running simulations and then there's also a code that's being developed within the goals team called Cafe, which is I guess a improved version of an old version of Cafe, which was run primarily on Spitzer data, and that was what the infra group had very successfully pieced apart all the different like pH features and different lines. But of course, with JWST, because of the better spectral resolution, we might even be seeing features that we have never seen before. So, hopefully this person would be comfortable, like kind of exploring in new territories, kind of using some of these new software and being comfortable with basically MIRI mid-infrared IFU data. So, and obviously happy to go even more into it if anyone's interested in particular.
Excellent, thank you. Are there any other questions from the audience? All right. Yeah, Misty, you still have your hand up, but it's from the last one, I assume. Yeah, okay. All right, well, I guess the one last question, since Shobita had to leave, I will ask you the obligatory question of what would you do with ORCAS in any of the different topics that you mentioned today?
That's a really good question. Obviously, I've been thinking about it since Shobita got us involved in the ORCAS project, and I think I'm hoping that it would be revolutionary in terms of the spatial resolution that it can get us. I'm excited about some of the ELT work that's coming, partially because of the resolution that we'll be getting. Of course, we can't exactly expect ORCAS to be too efficient in doing some kind of population size stuff, but it could be a pathfinder, right? It could be a pathfinder in demonstrating the capabilities of what we can do when we have that small resolution. So, especially in terms of these really near, I'm being careful with the distinction between binary and dual here. Mostly whether or not we're reaching down to the separations that are getting to the gravitational bound, whether black holes are going to emerge, but small separations that I'm hoping ORCAS will be able to at least find us some cases, at least in the electromagnetic windows, and that we can perhaps start to, cross-correlate with gravitational wave sources. But in particular, there's been a very limited number of binaries / very small separation cases that the community has accepted, right? We talked about 4C plus 37 before, and that has decent signal to noise, and that was I think at 7 kiloparsec. And there had been another paper on actually on one of these goals lurks, that's NGC 7674, where supposedly the VLBI imaging can get down to sub-parsec. I think it was like point something parsec separation. And I guess it obviously, with all these discoveries, there's a lot of healthy skepticism that is brought up. And I think it's good that we were seeing these things, but it's also good that we are questioning ourselves. Are these actually true? And so we need multiple validations. And I think ORCIDS can hopefully provide one such aspect of this critical validation that we need across the board. So, yeah.
Yeah, great. That's a very good point. All right, well, I want to thank everyone for coming, and especially Vivian for a great talk. And next week is our last talk of the series, and Erin is going to be giving a talk. And so I hope to have everyone back. And yeah, thank you so much for keeping the talk very short. So now we were able to ask questions for a long time, and we still finish early. So thank you, Vivian.
Thank you. And thanks everyone else for coming in.
Thank you for the nice talk. Have a good weekend.
Thank you too.
Thank you.
Thanks, Vivian.
Thank you. Okay.
Okay.